Welcome to this lecture on groundwater with Darcy and Bernoulli. Darcy lived in the 19th century, Bernoulli in the 18th century. Understanding the equations or laws that they derived is fundamental to understanding groundwater hydrology. Groundwater is important as effluent seepage leaving a groundwater body that feeds streams, rivers, wetlands, and lakes, for agriculture, the growth of crops, as an often clean source for drinking water, for many industrial activities, and for the sustainment of biodiversity in groundwater-dependent ecosystems. Groundwater is a valuable resource that needs to be protected from pollution and overexploitation. Let's start off with a little quiz, a multiple choice question. By law of nature, water flows from a higher to a lower A elevation. Is that the right answer? Or is the right answer, by law of nature, water flows from a higher to a lower B energy? Or does water, by law of nature, flow from a higher to a lower water pressure? C, pressure. Or are D, all of the above options true? Think about this. There is only one right answer. Which answer is right? To start off, we first need to explain the positioning of the water table in easy terms. If you were able to dig a large pit, the level to which the water from the ground rises in that pit is called the water table. The water table is in between the unsaturated zone, with soil water, water and air in the soil pores, and the saturated zone or groundwater, water in the pores. A water table that can establish itself freely is by definition the level at which the pore water pressure in the ground equals the air pressure of the overlying air. On average, this air pressure is the standard atmospheric pressure of 1 atmosphere, which is 1013.25 hectopascal. Instead of using this a little bit awkward standard value as the average water pressure at a free air-water interface, such as this water table, it is common practice to define the water pressure at a free air-water interface as 0. Thus, the water pressure has a value that should be interpreted with the existing air pressure at the air-water interface as a reference. And a 0 water pressure means that the water pressure equals the existing air pressure at the air-water interface. This is what we commonly do in hydrology. We simply denote the water table as having a relative water pressure 0, or in short, as having a water pressure 0. When we move down into the groundwater, we have positive water pressures, and when we move upwards from the water table, we have negative water pressures. This photo shows a model between two glass plates. The glass plates are 5 centimeters apart. The space between the glass plates is filled with gravel and sand. In reality, this makes for sand and clay layers. The model is 75 centimeters high and 1.5 meters wide. The model is a replica of the subsurface, being 80 meters high and 13 kilometers wide. To the left, we have a higher part of the landscape, and to the right, we have a lower, flat part of the landscape. It rains, as you can see at the top, and water moves out of the model in a small stream in the middle and a river to the right. From the back of the panel, a coloring dye is injected into the system at 2 locations, here and here. This enables us to follow the groundwater flow pathways. The water table is approximately as I'm now indicating with the pointer. The water table coincides with the surface water level at the stream and river. We see that groundwater from the left flows in this manner through these two clay layers and then into this river. We call this a regional flow line. At the top of the subsurface, we can see the movement of the groundwater along a local flow line. Let's take a better look. What do we actually observe? First of all, we see that in this setup of phreatic or unconfined groundwater, as it's called, groundwater flows along curved pathways. Be it that the curvature in this model is exaggerated as the vertical height is exaggerated in comparison to the horizontal distance. Secondly, we see at the discharging end of the regional flow line that water flows upwards from a lower to a higher elevation. So there's no problem in that. Rivers may be fed from the groundwater below. Because the column of groundwater is larger when we are deeper down in the subsurface, the water pressure is larger deeper down. Thus, we observe at this discharging end that the groundwater flows from a higher to a lower water pressure. If we look at the recharging end, we see the opposite. Groundwater flows downwards from a lower to a higher water pressure. So there's no problem in that too, as well as from a higher to a lower elevation. In conclusion, groundwater can flow from a higher to a lower elevation, from a lower to a higher water pressure, but also from a lower to a higher elevation, from a higher to a lower water pressure. So we know now for sure that two of the options in the multiple choice question, by law of nature, water flows from A, a higher to a lower elevation, and C, from a higher to a lower pressure, are not true. This also rules out option D. All of the given options are true. By law of nature, water flows from a higher to a lower energy. Answer B. Daniel Bernoulli is a Swiss mathematician and physicist born in the Dutch city of Groningen. To better understand the physics behind groundwater flow, let's continue with Bernoulli's principle. Let's first take the example of water flowing through a garden hose. Water molecules collide with the inside of the garden hose, building up static pressure. If the water moves slowly, we have many collisions and a higher pressure. If the water moves fast, we have fewer collisions and a lower pressure. In fluid dynamics, Bernoulli's principle states that an increase in the speed of a fluid, here water, occurs simultaneously with a decrease in static pressure or a decrease in the fluid's potential energy. Another well-known example is provided by air rushing around the wings of an airplane that is speeding up on the runway. The wing's upper surfaces are curved, causing the air rushing over the top of the wings to speed up, which decreases the air pressure above the wings. The pressure on the top of the wings, then, is less than the pressure on the bottom of the wings. The end effect being that the wings are lifted and that the plane takes off into the sky. Although Bernoulli deduced that pressure decreases when the flow speed increases, it was Leonhard Euler, also a Swiss mathematician and physicist, who derived Bernoulli's equation or law as we know it. A water particle moving along a streamline possesses three interchangeable types of mechanical energy: all in joule. Kinetic energy, potential energy, and pressure energy. M is the mass of water in kilogram. Small v is the velocity in meter per second. G is the acceleration due to gravity in meter per second square. Z is the elevation in meter. P is the pressure in joule per cubic meter or Newton per square meter. And large V is the volume of water in cubic meter. If there is no loss of mechanical energy due to friction, and if we take water as incompressible, then Bernoulli's law for steady flow states that the sum of these three interchangeable types of mechanical energy is constant, a notion also known as conservation of energy. Bernoulli's law is also sometimes referred to as the energy equation. As flow velocities in groundwater are observed to be very slow, I'll come back to this later, the first term, the kinetic energy, may be neglected, and thus for groundwater, mgz plus pv is constant. By dividing all terms to the left and right of the equal sign by the volume, large V, we obtain an expression per unit volume of the water. Mass m divided by volume, large V, becomes density. So ρgz plus P is constant. Because fresh groundwater has a constant density of 1000 kg per cubic meter, we can also divide by the density. And because g, the acceleration due to gravity at a certain location, is also constant, we can also divide by g. This delivers the following equation. Z plus P divided by ρg is constant, in which all mechanical energy terms are presented in the length unit of meter. Z is called the elevation head, P divided by ρg the pressure head, and the constant length unit to the right of the equal sign is the total energy with a length unit, the hydraulic head. We can quite easily measure the hydraulic head by using a so-called piezometer, which is a tube often made of PVC with a diameter of 20 to 50 millimeter and with a short screen of 10 to 30 centimeter length at the bottom, placed under the water table, through which groundwater enters the tube. Groundwater can only flow into the piezometer through the screen at the bottom of the tube. The hydraulic head is thus measured at the location of the piezometer screen. Z is the altitude of the screen above the reference level in meter. P divided by ρg is the water pressure above the screen in meter. And by adding Z and P divided by ρg together, we obtain the hydraulic head in meter, the total energy as a length unit at the position of the screen. In this figure, we see a phreatic or unconfined local groundwater flow system in cross-section. Here we have the surface of the land, the water table, a river or canal, and two pairs of piezometers at two locations with their screens at different depths. If we take the bottom of this picture as our reference level, the hydraulic head measured at this piezometer screen is simply this height, which I'm indicating with the pointer. And for this piezometer screen at this location, the hydraulic head is as I'm indicating now. So we have a higher hydraulic head, a higher total energy here than here, and also a higher total energy here than here. Water is flowing downwards here, and upwards here. Of course, with this right pair of piezometers, you must take care that there is no leakage from the water in the river or canal alongside tubes. Important to mention is that for measuring the hydraulic head at the location of a piezometer screen, we must use a piezometer with a short screen, whilst for measuring the position of a free water table in a tube, to mimic the level to which groundwater would rise in a large open pit, remember the earlier slide, a tube should be used that is perforated, thus acting as a screen all the way from bottom to top. If we were to install more piezometers, we could establish these streamlines of the groundwater. Here it's recharging and here it's discharging into the river or canal, as well as the broken lines of equal total energy or hydraulic head. These so-called equipotential lines are perpendicular to the flow lines for steady groundwater flow, which is defined as groundwater flow for which the flow velocity components at any location do not change with time. So this is a higher hydraulic head, this is a lower hydraulic head, and this is an even lower hydraulic head, etc. Again, water always flows in the direction of the lower total energy, the lower hydraulic head.